Well, there are properties of the directional derivative that are definitely worth a look, and all these properties are theorem 13.11, 13.12, and some more besides those theorems. So for the directional derivative, with theta, the angle between our direction unit vector, u, and del f, then the derivative of f in the direction of u is del f times, or I should say dot product with the unit vector, which is the length of del f times the length of the unit vector, of course that's 1, times cosine of theta, where theta is the angle between. And so since the length of the unit vector is 1, that just simplifies as the length of the gradient vector del f times cosine of theta, where theta is the angle between the gradient and the direction vector. So what does that tell us about the value of the directional derivative in that direction? And think about it. Cosine of theta, the very largest that could be is 1. And that can only be 1 if the cosine of theta is the cosine of 0. So see, that means when our directional derivative is a maximum, then the directional derivative is the length of the gradient vector, and that maximum derivative occurs when the gradient is pointing in the direction of that unit vector. So the angle between them would then be 0. So another way to say this, the gradient always points in the direction of steepest ascent on the surface. In other words, if I'm climbing a mountain, and that mountain has some surface generated, function of 2 variables, then if I'm on that surface and I want to see the direction of steepest ascent, I would find the gradient of that vector, and I would say that gradient, I would find the gradient vector, and that gradient vector would point in the direction where going up the mountain is steepest. So f increases most rapidly in the direction of the gradient. So the gradient gives us some information. Where is this function increasing the fastest? In the direction of the gradient. And of course it's decreasing most rapidly in the opposite direction of the gradient. And we could probably guess that the derivative in the direction of negative the unit vector is negative the directional derivative in the direction of u, the unit vector. So that seems very logical, and it's true. So the relationship of the partial derivatives to the directional derivatives are partial of f with respect to x is the directional derivative in the I direction. Partial derivative with respect to y is the derivative in the j direction. So any vector normal to the gradient is a direction of 0 change in f. And that means if I'm on the side of the mountain and maybe I'm facing directly up to the peak, that if I turn directly to my right or to my left, then there'd be no change. So it's kind of like if you want to walk around the side of a mountain, then you're not walking uphill or downhill. And that would be normal to the direction of steepest ascent, that's the gradient. Or you could also say normal to the direction of steepest descent, and that's the negative of the gradient. So that would be a direction of 0 change. And if you think about it, what that says is the cosine of the angle between the vectors would be pi over 2, because cosine of pi over 2 equals 0. And that means the gradient is normal to that unit vector we're looking at. So also the gradient vector is normal to the level curve at P, That's interesting. So if this is our gradient vector, and these are the level curves of this function, I hope you can see from that that this gradient vector is normal to that level curve. How about that?